So I'm very honored to be the chairman of this session, and I'm very pleased to introduce you our colleague and friend Giuseppe Pucacco, who is a collaborator in all our projects since a long time ago, but is a fresh member of the PRIN, and so as a newcomer in the PRIN project, he will deliver a seminar on normal forms for the Laplace resonance. Usually is next corridor, so usually at the end we would go for a coffee, and I guess it is not possible. Okay, but it will be a pleasure to listen your conference. Okay, and please mute the microphones.
Okay, thank you, Ugo. It is a great pleasure to have the opportunity to deliver this talk in this beautiful series of the I-CELMECH seminar series. After the talk, there will be, I hope, a virtual coffee. The motivation of this talk is to illustrate some of the recent results that we obtained in the framework of the scientific activities that we have in support of the JUICE mission. This is work which is supported by the Italian Space Agency. And as you probably know, the JUICE mission is a mission planned for 2022 with the aim of exploring the Jupiter satellite system, especially the icy moon of Jupiter, Europa, Ganymede, and Callisto. And so we are interested in the orbital structure of the Jovian system, which is very, very interesting. But in this talk, I will also offer you some hint about applications of these ideas also for other kind of systems, for example, for exoplanetary systems. So the aim, the main subject of the study is the study of multi-resonant 1+n body gravitational systems. All of you are familiar with the case of mean motion resonance between two bodies, for example. Here we are interested in the case in which there is mean motion commensurabilities among three or more bodies, secondary bodies orbiting a central great planet or star. So let me remind the notion of mean motion resonance. We define a mean motion resonance when there is a commensurability between the mean motion of three or more bodies. In particular, we define this commensurability as pure when there is no possibility to decouple the main resonant relation into subsets of this kind. But this is just the case that we are interested in, actually, because it can seem trivial, but actually the dynamics is not so trivial and is very interesting, and is essentially what is called, at least in the case of, I don't know if you see the full screen. Ugo, can you check, please? Do you see my full screen?
Yes.
Yes. Okay. Sorry. So the case in which that we call Laplace resonance is the simplest case in which we can break the commensurability relation into a chain of two relations of this kind. This is the simplest case in which we have a commensurability of the form 2 to 1 2 to 1. And this is the famous case of the Galilean satellites, in which we have that the ratio of the orbital periods is just of this quantity. There are other possible cases that are called Laplace-like resonances. And here we can see yes, we can see some examples of systems in which we have both the Laplace resonance, for example, the Galilean system, and also quite well-known exoplanetary system, which is called G876, which will be the subject also of some application later, and other cases also with some examples in exoplanetary system with different chains of resonances. So the first thing that I would like to illustrate to you is a model, is a toy model, very simple, a Newtonian model, which is essentially an extension of classical models studied by Sinclair, Henrard, and Malhotra in the past years. That captures the essential properties of the system with the simplest setting. The setting is essentially that of taking into account the Keplerian interaction of the secondary bodies with a large central spherical, for the moment, mass, and the disturbing functions that take into account the coupling, the gravitational interaction of the secondary bodies, but truncated to the first or at most the second order in the eccentricities, and average with respect to the mean motion, essentially, to the fast variables of the system, in order to limit the presence in the disturbing function only of the resonant terms, the terms that are characterized by the resonant combination of the angles that appear, that describe essentially the commensurability. We actually perform some further simplification, and this is already in some sense is the construction of a first normal form, in the sense that the Keplerian part is expanded in this form here in order to facilitate the algebraic manipulation of the model. This is a way to get a polynomial expression for the Keplerian part, and then we add the resonant part, which essentially is a function which is truncated to the second order in eccentricity. Here I reproduce only the first order, where we see the surviving resonant combinations of the angles, which describe the coupling of the three bodies. We can see that here appear these coefficients, which are the Laplace coefficient, but that must be computed taking into account the proper ratio of the average semi-major axis. Actually, we use a Hamiltonian approach, so the variables that we actually use are the canonical variables. So we introduce modified Delaunay variables, and so this can be introduced by these relations here. Then, in order to further simplify the model, we have to choose a set of variables which are adapted to the resonance, and this is a variant of this the resonant variables, which is a little different from the ones that were introduced by previous workers, essentially Enrard and Malhotra. And the difference is in the fact that the action variable, which is conjugated to the Laplace argument, that is the classic combination that we have seen before, is defined only in terms of the L actions, and this has some advantage that we will see later. So in this way, we can express the model in terms of these resonant variables. And we see that the choice of this variable has the first advantage, that the Hamiltonian does not depend on the angles conjugated to the two combination capital Q5 and capital Q6, which in this approximation, at this order, are integrals of motion of the system. So we have reduced the dimensionality of the problem from 6 to 4 degrees of freedom. These integrals of motion are used to define these two frequencies, K1 and K4, which appear in the linear part of the Hamiltonian, and are clearly function of the initial conditions of the problem, as usual. So are fixed in some sense by the choice that we want to do in order to describe the structure of the system. The system is then described also by a set of parameters. Here, these are essentially the first coefficient in the expansion of the Kepler part, and from this coupling constant, which it is important to remark, depend on the mass ratio, and so are small quantities if clearly the mass ratio is small, in the sense that it is the ratio between the masses of the satellites over the mass of the planets, or the planets, or ratios of masses of planets over that of a star, for example. Then we can, in this way, further simplify the system if we use Poincare variables in place of the Delaunay variables that we introduced before. And also we can make an ordering of the Hamiltonian, which takes into account of the smallness of the various terms that appears. We already have seen that there is one source of smallness in the fact that the disturbing function is first order in the masses. Then another source of smallness, we can say, is to assume for the moment that the eccentricities of the orbits are small. And so we can say that this chain of oscillators here are second order, essentially, in the eccentricities. And so we can say that the Hamiltonian is naturally ordered in a bookkeeping in which the zero order part is that given by essentially the L actions. The second order part is given by the eccentricities and the mass ratio. So this is a quantity of second order and higher order terms. And so the model, in some sense, is a model of a chain of harmonic oscillator coupled to a pendulum, essentially, in which the angle of the pendulum is just the Laplace argument. And so in this way, it is quite simple, first of all, to investigate the equilibria of this system. the equilibrium of this system actually correspond to periodic orbit of the original system. And in this setting, to compute the equilibria is really very simple, because we remember that essentially we have a chain of harmonic oscillators perturbed, or better say, forced by constant forces, maybe with a small modulation due to the Laplace angle. But essentially, these oscillators are displaced by these linear terms in the potential, which gives constant forces. Therefore, the equilibria of these oscillators is in some points, and these points are essentially given by the ratio between the coupling constant and this slow, or slow frequency, we can say, which appears here as a combination of the two frequencies that have been defined before. And it is important also to note that this frequency omega, which appears here, is also defined in terms of the L variables, and so essentially the initial conditions. In principle, one could think that a good choice is to use, to define this frequency here, the nominal resonant value. But if one uses this frequency, turns out to be exactly 0. And so it is usual to choose as reference value values dictated, for example, from the observation, or not exactly close to the resonant combinations. Another important aspect of this equilibrium solution is that, since we remember how the x and y variables are defined, it gives not only the amount of essentially the forced eccentricity, which is related to the value of this equilibrium, but also the value of the resonant angle, because the sign of this quantity says if the center of libration, which is associated to this point, is 0 or pi. And so by a very, very simple approach, we can compute analytically a prediction. Here I put this to indicate that this prediction is computed with this first order toy model, let us say. And so the prediction gives the value of the forced eccentricities and the value of the center of libration of the resonant angles. And for example, in the case of the Galilean system, you can see that there is a quite good agreement. The only disagreement is the fact that the true Galilean system, the third resonant combination, is rotating. But actually, this is not a disagreement, but simply the fact that the forced value of the eccentricity here is quite small. And then the oscillator has an amplitude of oscillation that is big enough in order that actually the argument of the Poincare variable is not librating but rotating. But this does not break the equilibrium of the system. These equilibria are called usually de Sitter equilibrium, but I prefer to use to attach also the paternity to Sinclair, because it was Sinclair who gave the most complete analysis of this kind of equilibria. And I also here report the second order model, in which I also added some other refinement of the model that I will describe later, where you can see that the eccentricities that the model can predict are quite close to the one that are observed in the real Galilean system. So one is tempted to apply the same model to, for example, the famous G876 system. Famous, it is a system which is quite famous among people working in extrasolar system, but maybe it's not familiar to all of you. So I just remind that it is a system which is quite close, so it is very well understood. It is a dwarf star, slightly smaller than our sun, surrounded by a planetary system with three giants. Two of them are of the masses which is more or less comparable to that of Jupiter. And the third one is a Uranian mass planet. And this system is packed in a region quite small, more or less of the size of the orbit of the Earth, essentially, but with some giants in place of our terrestrial planets, locked in the Laplace resonance, but with, as you can see, a large value of the eccentricity of the first planet. And I was a little disappointed when I tried to apply the equilibria computed in the toy model, and I found that both the eccentricities and the centers of libration were completely wrong. Completely in disagreement with the observations. And since the observations are quite good, I asked myself how one can reconcile a model with the observation. And the idea is essentially the fact that actually the model must be modified in a very simple way, actually, because one has simply to remove the condition that the eccentricity are small. Essentially, the perturbation approach can be maintained, but the expansion must be done only in the masses and not in the eccentricities. So in place of the equilibrium that we computed before, simply of a displaced linear harmonic oscillator, we will have a set of nonlinear harmonic oscillators. And we can give a very simple solution if we do the assumption that only the first of these oscillators has a big amplitude. Let us do this very simple approximation, because this approximation can be solved analytically, essentially. In place of the linear equilibrium equation for the oscillator, we have a nonlinear equation to solve. This is a cubic equation. Clearly, for a cubic equation, we have an exact solution, but we can also approximate this solution with this simple trick. We can solve for the part which does not depend on the perturbing parameter. The solution of the zero-order term is immediate. And so we can obtain an approximate solution taking into account also the perturbation. And so we get these additional two equilibria, which can be used to compute also the additional new equilibria for the other two degrees of freedom. Just to get a mechanical interpretation of this system, is like if you pass from an oscillator, an harmonic oscillator like this, with the equilibrium which is displaced from the origin, to a nonlinear oscillator in which one has that the quartic terms are dominating, and so one has two new equilibria displaced from the origin by some large value. And if we come back to our table, we can see that with this very simple assumption and with the computation done in this perturbing way, so it is just an approximation, you can see that the eccentricities of the G876 system are quite well reproduced, and also their center of libration are reproduced. And I have to say that these centers of libration are actually really strange, because they are completely different, as you can see, from those of the Galilean system. And so the equilibrium structure of this system is really quite strange, because it has some conjunctions that apparently are really prohibited in some sense, no? Because one is acquainted with the conjunctions that are usual in the Galilean system. But this is what the model in this case predict, and this is what the observational fits give. Okay, so this is the first interesting result that I would like to give to you. And in addition to this, I would also remark that the stability of these equilibria can be studied in the framework of this model in a very, very simple way, because the matrix that one has in the variational equation can be written explicitly, and the eigenvalues can be computed explicitly. And what is interesting is that one can prove that all eigenvalues are pure imaginary if the frequency that we introduced before is greater than some limiting value. And this is an analytical confirmation of a result that Yoder and Peel obtained numerically several years ago. Okay, and now, a second interesting application of this approach is to study the dynamics of the librating part of the resonance. So one can perform a further simplification, if you want, of the Hamiltonian, in the sense that one can construct a normal form in which one, from the Hamiltonian that we saw before, eliminates the angles which characterize the libration of the eccentricity part, let us say. So if one performs a normalization around the equilibrium of the Q4 action, one normalizes essentially with respect to the isotropic oscillator that we saw before, and so construct essentially a modified pendulum Hamiltonian, which describe the libration in the phase plane of the Laplace resonance. And clearly, with this very simple Hamiltonian, one can compute the first approximation of the libration frequency. This is essentially the frequency of libration around the center of the Laplace resonance, and also the width of the resonance, which turns out to be quite small. This is just the case of the Galilean system. And on the left, you see the phase plane of this pendulum, and on the right, integration, a numerical integration of a certain libration of the system, and one can check that the analytical phase curve reproduces quite well the true evolution of the system. So how can we apply in concrete the tools that we have introduced? I can show you a first application, which is quite nice, because it is essentially a very simple extension of the model, because if you remember, in our original Hamiltonian, we have taken only the purely Keplerian part. But for example, in the case of Jupiter, we know that the oblateness of the body of the planet is is not negligible, and this is the reason why the precessions, there is an extra precession of the perigeuls, of the periastron, and this can be added to the frequency that we introduced before. And so the idea is essentially that by adding this contribution, this secular contribution due to the J2 essentially of Jupiter, we have that our chain of oscillator now is anisotropic in some sense. This frequency break the isotropy of the frequency here, and so we can take into account of this, but since this breaking is quite small, we can still construct a normal form, which we call a detuned normal form, in the sense that is still constructed by keeping the resonance, and so keeping the dependence on the angle like before, but with coefficients that now depends on the modified frequencies. And what is really very nice is that constructing a normal form in this way, by going to a quite small order, even a second order computation, one can predict analytically the periods of libration that we get here. Here are the periods predicted by the toy model that we saw before. So we see the isotropy of the frequencies. Here we see the modification of the frequencies. These are the period of the librations of the free eccentricity of the three satellites. And this is the period of the libration of the Laplace argument. And here is compared with a very accurate numerical model. Is an ephemeridess model published recently. And so one can see that a very simple normal form construction gives a quite accurate description of the true, let us say, Galilean system. And as a second application of these tools, here is some consideration about the fact that clearly these systems are not purely Hamiltonian, because we know that there are interactions that involve the structure of the bodies that are involved here. There are several effects. For example, in planetary systems, we have interaction with protoplanetary disks and other dirty effects, which are quite complicated. But there is an important phenomenon which is quite general, both in planet-satellite system and in exoplanetary system, and this is clearly the tidal coupling between the central body and the orbiting bodies. And essentially, the main phenomenon that we have is that this tidal coupling produces a variation of the Keplerian elements, and above all, a variation of the semi-major axis and a damping in the eccentricities. And the parameters that enter into these equations are related with the structure of this body, these bodies. For example, in the case of the variation of the semi-major axis, the ratio between the log number, which describes essentially the elasticity of the satellite and excuse me, the elasticity of the planet, in this case, of Jupiter in this case, and the dissipative part, which is described by the quality factor, gives the rate at which the semi-major axis change. And here, instead, it appears the time scale on which the damping of the eccentricity happens. But what is really most important in this expression is the fact that the variation of the semi-major axis is governed by the sign, is governed by the relative value of the spin velocity, of the rotation velocity of the central body with respect to the mean motion of the tide generating body, let us say. And so there is a fundamental difference between the case in which the central body is rotating fast, let us say, this is rotating with an angular velocity which is greater than the mean motion of the tide generating body, because in this case, this quantity is positive, and so semi-major axis increase. This is typically the case of the Earth-Moon system. The increase in the semi-major axis is accompanied by an increase in the angular momentum of the orbital motion at the expenses of the rotational velocity of the planet. In the other case, in the case in which this sign is negative, this is typically the case of a slow rotating central body. And this is typically the case of a star. So in a planetary system, we can expect that usually the semi-major axis decrease. But here I put in the adjective usually, because this is not all the story, because there is the case in which the system is characterized by multi-resonant motion, then we can have an extra effect which is related just to the resonance of the system. And here, to understand what is going on, it is still useful to still use our simple model of the oscillators. Now the harmonic oscillator is forced and damped. The damping is essentially the damping due to the tidal coupling. So you see that the equilibrium value is like before, but we have also a small difference in the center of libration, because this is essentially zero when there is no tidal interaction. And this center of libration, even if small, is enough to drive a possible extra variation of the semi-major axis. That is, what happens is that, for example, take the first of these of the bodies, for example, Io, in the case of the Jupiter system, we have that the tidal coupling would give an increase of the semi-major axis, but the resonant value of the center of libration, which is different from zero and is negative, can produce a temporary inward evolution of the semi-major axis. And this is confirmed by this simulation. We can see that these are L1, L2, and L3, that is essentially the semi-major axis, or the square root of the semi-major axis of Io, Europa, and Ganymede. And here we see that Io temporarily shrinks the semi-major axis and then takes again the trend in which it grows. And what is important, the growing of the semi-major axis is in such a way to keep the ratio that keep the Laplace resonance. And to confirm this evolution, here there is this quite nice plot here, in which you can see the damping of the free eccentricities, which is essentially the blue curve, and also the decrease of the forced eccentricity, which is due to the fact that the denominators in the forced eccentricity here increases in absolute value. Usually it is negative, but it increasing in absolute value. And this fact is confirmed by the fact that the omega frequency essentially is the oscillation of the free part of the eccentricity. And this can be seen by these two plots here. On the left, it is the oscillation at the start of the simulation with a certain period. And you can see that at the end of the simulation, the period of the free oscillation is much less. And this is in agreement with the fact that the frequency here is increased. So the forced eccentricity decrease, and you can see that the green curve is exactly the analytical prediction given by this formula compared with the numerical integration that is given by the blue curve. So this is a hint that the tools that this model provides are useful in describing the evolution of the system, which is driven both by the tidal coupling and by the resonant dynamics, which is coupled to this dissipative effect. Another nice thing that I would like briefly to show to you is the fact that the action that I have introduced before can be used as an adiabatic invariant, because one can see that this quantity in the course of the evolution after the transient stage stays more or less constant. And here is a nice plot in the phase plane of the capital lambda and small lambda, the action and the libration angle, in which one can see that the libration of the Laplace argument damps arrives to a minimum, which is essentially the minimum here, and then slightly climbs this tornado shape figure. So using this idea of this action used as an adiabatic invariant, one can try to describe, to understand what is the mechanism of trapping in the Laplace resonance. So, for example, one can simulate the following simple exercise. Suppose that we have two of the satellites which are already in resonance, 1 to 2 essentially, and the third one, Ganymede, let us say, which is still not trapped. Then we can evolve the system, and at some time the ratio between the orbital motion of Europa and Ganymede arrives at the right value. We have trapping also of Ganymede, and the trapping is confirmed by the fact that the resonant argument rotates before the encounter and then starts to librates and with a damping. And this evolution can be described in a way which is physically enlightening in the plane of the normal form, essentially, of the lambda plane, in which one has a motion of the pendulum in which the motion is rotating before the coupling, before the trapping. This is the moment of the trapping in which the pendulum, which is on which the torque of the tides act, is such to revert the rotation of the pendulum, but also with the right amount of damping in such a way to trap into the libration. And in this way, one can also try to compute a probability of capture following the classical approach of Yoder and Peel and Herrard. And so one can find a function which depends on the structure of the internal properties, essentially, of the satellite. And so one can try to make some prediction about this, for example, the log number of the satellites, which is a parameter which has an important meaning for the evolution, for the structure and evolution of these systems. Okay, so here are the conclusions. So essentially, in the work we are doing, we are trying to characterize the transient evolution after the capture of the standard Laplace resonance that we know. But we are also studying the future evolution of the system, in which one can conjecture the trapping resonance also of a Callisto. There is a nice recent work by Larry and collaborator, and we are trying to reproduce their results in the context of our model, which is much more simple. Moreover, okay, here there should be much more to say for the application in exoplanetary system, but let me just say that this kind of study can be done also in exoplanetary system with methods that were recently introduced by Morbidelli and collaborators. And finally, let me also mention something that I did not touch, but that can be quite interesting, and this is to add in the model also the tides between, among the satellites, that even if very small, due to the resonant dynamics, can be important. Okay, so thank you for the attention, and my wishes for a definitely better next year. Thank you.
So, thank you, Giuseppe. It was a very nice talk. So we have time for questions.
Ugo, can I ask something?
For sure.
Very, very nice talk, and this is an impressive set of results.
Thank you, Christos.
Many congratulations to the whole group there. I have a question regarding in the case of the Gliese system, where you speak about the second equilibrium. It reminds me a bit what happens in the classical 2-to-1, let's say, resonance, in which you have a phase portrait that goes like the second fundamental model. So one of the equilibria is in zero, let's say, phase, and the other is in pi, which is precisely what you find. But there was one thing which you said afterwards, that all the equilibria of that problem are stable. If that was similar, I would expect to find one unstable equilibrium, at least in one side of this. Let's say the cubic equation, which you say, it has either one or three roots. So where does this go, this equilibrium, the unstable one?
Yes, Christos, this is a very, very interesting question, because it is still puzzling me, I confess, because me too expected to find two stable and one unstable equilibrium. But actually checking the stability with both analytical and numerical tests, actually I find that all of three are stable. And my explanation is the fact that actually the coupling with the other degrees of freedom is actually changing the representation that we have of the situation. So the potential that I introduced before is just a mechanical analogy to show what happens for for a single degree of freedom, but the interaction with all the other degrees of freedom is changing, probably in a non-linear way.
Your system is with how many degrees of freedom?
Is 4 degrees of freedom.
So you have all, let's say it's a 4 times elliptic equilibrium. I mean,
Yes.
all these equilibria.
Yes, yes. In fact, in all 3 of these solutions, all 4 couples of eigenvalues turns out to be pure imaginary. And actually the original solution, the original solution in the sense that is the solution that one gets in the first order model, was indeed stable.
Yeah, well, that's reasonable for the first order, yeah.
Yes, but the problem is that the first order model was incomplete in some sense.
It's true, but on the other hand, to have a bifurcation, let's say, of equilibria, you need essentially to get this omega through the value equal of 0.
Yes, I see your point, but I think that this is not a bifurcation.
Okay.
It is, or better, is a bifurcation, but if you describe this change by changing some extra parameter in some sense, which is essentially omega, the frequency of the free eccentricities.
Exactly.
Okay, so it is some external, let us say, parameter.
Mm-hmm.
Other questions or remarks?
Giuseppe, it's Christoph. Just
Yeah.
did you speak? Why did you use a different resonant actions? You started at the beginning that you modified a little bit the resonant actions, and can you detail a little bit more why you did that in comparison to the original work?
Yes. I did not write here the original expressions, but I can say very simply that the original choice made by Herrard and Malhotra was of an action variable which involves also the pk variables. So essentially the eccentricities. And this puts some problem because the L actions are big quantities and the P are instead small quantities. So in order to do this kind of study, you have to expand around some, you have to expand around some equilibria that you already don't know. And this puts a lot of algebraic problems. Instead, with this simple choice, you remove this shortcoming, essentially. And also the second advantage is that you can describe in a very simple way with this lambda normal form the dynamics around the Laplace resonance. So it has a double advantage. But it is a very is strictly related to the old choice. I mean, it's a very small change in some sense, but has technical advantages. I don't know if I answered the
Oh, thanks.
Other questions or remarks? So when we are waiting for other questions or remarks, I have a minor one, and about the extrasolar systems, the extrasolar system you discussed, so GJ876.
Yes.
Well, as far as I know, as far as I have experienced, inclinations play a major role. So as far as I understand, your model is planar, isn't it?
Yes, yes, a very good remark. Thank you, Ugo, because I forgot completely to mention this. It was written in some of my slides. Yes, here, but I forgot to say, yes, you're right, it is a planar motion, a planar model, but take into account that this is a good approximation for the Galilean system, but is also a good approximation for a G876 system because the fits of the data made with models in which inclination is included are worst, in the sense that they reproduce in a worse way the data that comes from the radial velocities of the observations. So a model with very small inclination is preferred in this case.
Okay.
Clearly, you are right. I mean, in several other examples, inclinations are important. And so clearly, yes, one should include them in a more complete model. I agree with you. Let us say that this is really a toy model. So
yeah, but well, I have to confess that I had a look to some papers on that system, and while you were speaking, and well, it is usual to consider planar models. Okay, and so maybe the Laplace resonance is a favorable configuration with small inclinations. Otherwise, maybe you have not at all a Laplace resonance. But okay, this is a point to
Can I add
investigate.
something?
Sure.
Yeah. So first of all, let me say that as it was mentioned at the beginning in the first slide, this work was started with younger people and very the previous years with Fabrizio Paita, and then with Mara Volpi, Sevi Carampozziu, and Christoph Lotka. And with them, we have a program which includes also the inclination. But nevertheless, the inclination does not count very much. And at the very beginning, I was discussing a lot with Silvio Ferrasmello. It is unfortunately that he's not here now. I think he would have enjoyed very much. The Laplace resonance is one of his favorite topics. And when I was saying, well, should we include the inclination? He wrote a book on that, on the Laplace resonance. So, and so I was asking him, should we include also the inclination? And then he was saying, well, you know, I am a planar guy, so I don't never include inclination, and I think that in this case it does not count too much. Right yesterday, Sevi Carampozziu showed some results about the Uranus satellites, where there is which is a case where one of the bodies, the satellites, precisely Miranda, the first one, has an inclination which is not negligible, that is something of the order of 4 degrees instead of the 0.0 something for the Laplace, the Galilean satellites and so. But online with Christoph and Sevi, we ran the program and we saw that in fact the inclination doesn't count too much. So the main parameter that counts is beside the masses, the eccentricity is the J2 of the body. The J2 is extremely important. It's so some resonances could not exist if you have a bigger J2, that is, which gives, of course, for those that do not know, J2 is the biggest spherical harmonic coefficient of the geopotential.
Okay, thank you, Alessandra, for your remarks. Clearly, I hope that people realize that this is a very stimulating subject with a lot of possible developments, both for the solar system and extra solar system. So there is a lot of things to do.
Any more questions? Well, if not, so let me thank the speaker again. Let me invite the speaker to show his last slide so I can join him in wishing everybody Merry Christmas and an happy and much luckier New Year.